Recording is started. Okay, so let's not wait more, because, for example, Gergő has to go half an hour from now. So let's start. Okay, so what's the topic for now? So the last time, the plan was to talk a bit about normalization proof, but only a little bit, because it's very technical and I think it doesn't make a whole lot of sense to talk too much about it, and then talk about Satory model of type theory. Okay, so and in relation to the normalization proof, what I want to give is kind of just an outline for canonicity versus normalization for simple type theory, and then maybe a bit about dependent type theory. Okay, so let's start with this topic. So let's take another look at canonicity versus normalization for simple type theory. So let's have a simple type theory, and it's a simple type theory, but with function types and booleans. So we have function types and bool, and what we want to prove. So canonicity for simple type theory means that every closed TM, I don't even have to write closed because it's in this in the type signature. So every closed TM with type bool is either true or false. So this is canonicity, and we only want to learn something about booleans because we already know by eta expansion that that every closed function is equal to a lambda expression. Okay, and in general, so for negative types, we don't want to prove anything because they are automatically canonical by the eta rules. But for booleans, we want to prove that every closed boolean is either true or false. And last week, Ambrus showed a way to prove this for dependent type theory, which is a bit more general proof. And the way that the proof works is that we say, so this is kind of just repeating what we learned last week, that if we have a context in the syntax, then what we want to get from a context is actually, it's a predicate on closing substitutions. So in this model, if I have a gamma, so if I have a gamma in the syntax, then the gamma m is going to be a predicate on closing substitutions. So every context becomes a predicate on closing substitutions. Every type becomes kind of a dependent predicate. So if I have any closing substitution, and I also know that the predicate holds for the closing substitution, and then I have a closed term of this type. So if I have a closed term of this type, then I want to have a predicate which tells me something about closed terms of this type. So predicate on closed terms depending on context. And then I can take this kind of model and just continue it. And for substitutions, I want to prove that every substitution preserves the predicate. And for terms, I also want to prove that every term preserves the predicate, so that if I have a term and I have a closing substitution such that the predicate holds for the closing substitution, then if I apply the substitution to the term, then I still get something such that the predicate of the type holds for it. So this is called a logical predicate model. And
are these predicates in set or in prop, or it doesn't
they
matter?
are in set. They are in set. And they cannot really be in prop. So there is some proof relevance, because already with bool, if something of type bool is either true or false, that cannot be in prop, because there is a choice like a true or false, between true or false. So it contains relevant information for bool. Okay, so this was dependent type theory, but in simple type theory, we can do a bit more in a kind of a separated way. So we can factor this canonicity for simple type theory to kind of more basic things, and we can also factor the normalization, and perhaps it's a bit easier to see what happens in that setting. So if we are in simple type theory, then we can use an idea which is a bit similar to normalization by evaluation for canonicity as well. So in simple type theory, we can say that we evaluate terms in the standard model. Then we can go back to the syntax in some ways. So in simple type theory, if I have a T, which is a Tm, if I have a closed term with type bool, then I can perform an evaluation in the standard model. So eval in set model, and then I get some Tm, let's call it Tm, which has type bool, but this is a meta-theoretic bool. And then I can simply go back to closed terms by saying that the true should be mapped to true and false should be mapped to false. So I'm mapping true to true and false to false, and that is the way that I can go back to the syntax. And this is kind of similar to normalization by evaluation, so you can call this canonicity by evaluation. And this is not the whole story, but this is part of the story. I just take a term, evaluate it in the standard model, and then go back to a closed bool. And we can already do this. We don't need anything else. Just this function on the top of the usual standard model. But if I do this thing, then I don't yet know that that from this thing I get that the original, like if this is true, so if the evaluated term is true, then the original term should be true as well. Right, so if I take an arbitrary term and I just evaluate it and look at this Tm, and I can look at the Tm and see whether it is true or false, but from this it doesn't immediately follow that, okay, in that case, the original term must have been also definitionally equal to true or false as well, because in the original syntax I can have more complicated terms which are not obviously reducible to something else. So what I can do is I take this evaluation in the standard model, but I also prove that the syntax is like syntactic terms are related to semantic values. So in simple type theory, it is possible to say that I'm just defining a relation between closed terms and semantic values. So if I have a TMA and I also have some AM, so this is the evaluation of the type in the standard model, then I want to define a relation between them. And if I have something like this A is bool, and then I have some T and I have some Tm, then I can define this relation to be like if Tm, then T equals true as T equals false. So this is kind of just the obvious relation between a semantic Boolean and a syntactic Boolean. So if the semantic Boolean is true, then the syntactic should be also true, and for false the same way. And I can also say for at function types, so I have some syntactic function and I have some semantic function, and in this case I'm saying if that for any T and Tm such that T is related to Tm, I also know that the application of F to T is also related to the application of Fm to Tm. So here I am just saying like the obvious thing, and here I'm saying this preservation of relation. So for simple type theory, I can prove canonicity in 2 steps. So first, I'm just defining the standard model. And in the second, I'm defining a dependent model. So this requires a dependent model of simple TT. And in the dependent model, so types are interpreted with this relation, and contexts are also interpreted as relations between closing substitutions and semantic context. So if I have a context, then I also get a relation from a context. So it would be like a substitution into, so for every gamma, I get a substitution into gamma, and I also have a semantic context, which is just a set, which is kind of the environment of values, and I also define it like this, such that it's just pointwise relatedness. So it's pointwise relatedness, because this is an environment of values, and this substitution is also just a list of terms. So it's a pointwise relatedness of a list of terms and a list of values, list of semantic values. And for terms, I want to say, for terms, I can prove that terms preserve this relation, and for substitutions, it's the same thing. Okay, and so for simple type theory, already for canonicity, we can do something which a bit looks like a normalization by evaluation, because first we evaluate, and then we show that if we go back from semantics to syntax, then we get there is some connection between the syntactic stuff and what we can get from the semantics, and the connection is given as a separate step by defining this logical relation model.
And sorry, just a quick question. Does this squiggly equal relation sort of include the how to say completeness and the stability of the normalization at the same time, or?
At this, so for canonicity, we don't talk about the completeness or stability or anything like that. It's not even defined for canonicity.
Okay, then it's not.
So it's only for normalization. So here we want to prove that that every T is either true or false. So if we do this additional logical relation between the syntax and the standard model, then we can use it to say that if we have a Tm bool, and then we get a Tm, which is just a bool by evaluation in the standard model. And but from this logical relation, we also know that T is related to Tm, right? And at the type bool, the relation exactly says that the original T must be either true or false, right?
Yes.
Okay, so this says that T must be true or false. So we get canonicity for T by using the meta-theoretic canonicity for the value of T, because the value of T is bool, and in the meta-theory we know that every bool is true or false. So we kind of reflect the canonicity of values into the canonicity of terms.
So really what you want, what you need to prove is not that terms preserve this relation, is that eval preserves this relation, right? That if I take the eval, so T is always quickly line to eval T, right?
Yeah,
Yes,
but the statement is a bit more general, so let's just write it out. So if I have a T, because terms can be in any context, right? So Tm gamma A, and what I want to show, so in the, okay, let's just write it out. So if I'm writing this just naively in Agda, then maybe there is a Tm squiggly function which takes a Tm gamma A, but I also need to have a closing substitution because this is in gamma, but my relation only talks about closed things. So I need to have a closing substitution and also some semantic context, and also that these are related. And then if I'm substituting T with sigma, I also want to know that this is related to evaluating Tm in sigma m. So this is kind of the general statement of this preservation, and I need to show this thing. And if Tm is closed, then as a special case, I get this, that T is always related to the evaluation of T in the empty context.
So this squiggly relation implies the completeness, for example, right? I know that you said that it's not really related, but completeness would state that if we completeness states that if we have normalization and we normalize and we transform the normalized value back into the object theory, then those two will be equal, right?
Yeah, I mean, yeah, you can say it. So yeah, we could say that completeness of evaluation in the standard model is the same thing as canonicity.
Okay.
Or it's logically equivalent to canonicity.
All right. Thanks. Sorry for forcing this, but I feel like I understand it more if I use the terms that I already know.
Okay, so this is actually very simple, but it's not a lot more complicated to do it like in type theory when the two steps are meshed into just one step. But the problem is that in type theory the two steps cannot be separated. So because I'm not sure exactly at what point it goes wrong, but it's a general phenomenon is that for time theory you cannot separate these two steps for canonicity, but also for normalization. So you have to mesh them together into. So here we are defining kind of the evaluation at the same time that we are defining these predicates, because this is a proof relevant predicate, so it already contains the proof relevant information, which is the same computation as evaluation in the set model, but somehow we cannot separate the two things, and we have to do the two things at the same time. And okay, so what about normalization for simple type theory in the, so this is normalization by evaluation. then we see that we are, again, we have an eval. So if I have a t, which is a tm gamma anything, then I'm doing an eval, but this eval is in a particular presheaf model. So it's in a presheaf model, and then I get a tm, which is so it's going to be some em gamma or whatever, and then we can use this so-called quoting, which goes back but into normal forms.
But wait, I have another question about the previous stuff, because I just now realized that if eval only works on closed terms, so then the tm on line 41, so that can't be, so I understand that t with sigma substituted by sigma is a closed term, right?
Evaluation works on any term. So evaluation into any model has to work on any terms. So, but then what happens is that if you evaluate an open term, you have to provide an environment which closes it down, basically.
Right, but it's just okay, but it's not okay. But what you're evaluating is still the open term, and then you're using the environment to evaluate it further, I guess. So because it's not, it's not, so it's not t with sigma applied and then you evaluate that, because that would be t sigma m, right? It's tm, which will be a mapping from the environment to a value, like on the right hand side, I mean.
So if t is tm gamma a, then tm, so evaluation of t in the set model is gamma m arrow am. So a term becomes a function in the standard model.
Right, from the environment. Right.
Yeah, so context becomes a type of environment, type becomes semantic type, and t becomes a function from semantic context to semantic type. And in this relation, it's a relation between the syntax and standard semantic values. So on the left-hand side, I have a syntactic substitution, like a syntactic closing substitution, and here is just a semantic evaluation into sigma. Okay, so for normalization, for simple type theory, so first we evaluate in a presheaf model, but in certain kinds of presheaf models, so not any presheaf model, but the kind that works for this purpose, and then we can go back from semantic values to normal terms. And this thing works in arbitrary gamma context. So this canonicity by evaluation only works on closed terms, but this works on arbitrary terms. And that's the main reason that evaluation in the set model is not workable anymore. So it is not possible to just evaluate in the set model and then go back to normal form, because it doesn't contain enough information. So just intuitively. So why can't we quote from like set model values to normal forms? So why can't we just use a set model to get back to normal form? And the reason is that we cannot go under any binders in the set model. So we need some way to get kind of fresh variables. So if I want to summarize the problem very shortly, the problem is that we need a source of fresh variables to go under binders, right? Because if I have a semantic function, so if I have some f, which is a semantic function which goes from a semantic A to a semantic B, then the goal would be to get some NF gamma A arrow B. But here I'm kind of forgetting about this gamma. So actually here, like a semantic function also depends on some semantic gamma. But just to be a bit hand-wavy, so here what would happen is that I need to produce a lambda for the goal, which is a normal form. And here I would want to produce an NF gamma AB. But the problem is that if I have a semantic function like this, the only thing which I can do is to call it with the semantic AM. And for example, if this is a bool arrow bool function, and we want to get a bool arrow bool normal form out of it, the problem is that if you have a semantic bool arrow bool function, you can only ever call this function with a concrete true or false, and then get a concrete true or false. So only call with true false and get true false. And from this information, we have absolutely no idea what the body of the function should be. So the true solution would be is to call f with a fresh variable and then get back something which is not just true or false, but which has a bit more structure. Like, for example, it could be also a neutral bool expression. So if you know about like the Haskell implementation of this quoting and normalization, then the way it works is that whenever we want to go under a binder, we have to pick some variable which is fresh relative to the current context, and then get back some semantic value. But the semantic value can be also neutral. So it's not just a canonical meta-theoretic value, but it can contain actually variables, which makes it possible to reconstruct a normal form from it. So the problem with the set model is that it has absolutely no information related to variables and fresh variables and neutral values. And by moving to the species model, we can kind of fix it by adding the extra information relative to the set model. Okay, and what is the species model? So the species model is, so what is the base category? The base category, it has to be the syntactic, so it's a syntactic thing. It's not exactly the syntactic category, but it's the category of syntactic renamings. But it also works if we say that embeddings. Okay, and what is a renaming? So what's a renaming? So a renaming from gamma to delta, let's just call it a ren gamma delta, is a substitution from gamma to delta such that it only contains variables. So a substitution from gamma to delta is a delta long list of terms, and the renaming is a substitution which is a list of variables. Okay, and what is an embedding? So what is an embedding from gamma to delta? It's also a substitution. So it's a substitution from gamma to delta. But actually, we don't necessarily have to talk about substitutions to define embeddings, because we can just say that there is an embedding from gamma to delta if if we get delta by dropping 0 or more entry from gamma. So an embedding from gamma to delta actually means that the delta context can be embedded in some way into the gamma context. So, like for example, if gamma is bool, not bool, and then if delta is not bool, then we have an embedding from gamma to delta, which is defined by dropping the first entry from gamma. So let's drop first entry from gamma. And the information in an embedding is actually kind of just a list of booleans. So it's kind of a bit mask, which says that which entries we want to drop from the gamma context to get delta. But in dependent type theory, it's more restricted than just a general mask on the context, because we also have the requirement that the delta should be a well-formed context. So we can only drop things from the context such that all the types which can depend on each other. Like, so this is a dependent context, and in dependent type theory we can only do embeddings which return or not return. So we can only have embeddings such that gamma is well-formed and delta is also well-formed. So it's more restricted than just having a bit mask on gamma. Okay, and then we can have categories of renamings and embeddings, and because every renaming and every embedding is just a substitution, these are just subcategories of substitutions, and we can compose them the same way. And so it's pretty easy to see that if you have restricted substitutions, okay, not arbitrary restricted substitutions, but renamings composed to renamings and embeddings composed to embeddings. And there are also identity renamings and identity embeddings. And they are all subcategories of the category of substitutions. Okay, and then we can say that we want to take the pre-shift model. So pre-shift model over the category of renamings. So I could also say that this is category of embedding. It doesn't really matter, both words. And okay, so what happens if we want to evaluate a term? Let's just stay in simple type theory in this pre-shift model, right? So if I have a T, okay, let's make a bit more. So if I have a type and I want now to evaluate in the pre-shift model, then I get something which is a pre-shift over renaming. If I have a context, I also just get a pre-shift over renaming. If I have a term, then I get a natural transformation. So this is going to be a natural transformation between gamma and AM. And it is also often helpful to use this notation. So whenever we are talking about pre-shifts, it is kind of helpful to use the notation of components of the pre-shift model of type theory already. So it becomes a bit self-referential, but it actually makes the notation much easier. So we could say that the context in the pre-shift model is just defined to be a pre-shift. So a conem is just a pre-shift over renamings, and then a time is just defined to be, I mean, in the presheaf model of dependent type theory. So this would be some kind of dependent presheaf over gamma. Over gamma, and the substitution from gamma to delta is, so this would be the natural transformations, and then the Tm from gamma to A would be kind of the dependent natural transformations. But this comes from the presheaf model of dependent type theory. But here I'm just want to define what happens in the presheaf model for simple type theory. But already I can reuse these notions. So like I could as well say that from a type I get a context internally to the presheaf model of type theory, and from a context I also get a context in the presheaf model, and from a term I get a substitution in the presheaf model. Yeah, and if I have a substitution in simple type theory, then so in simple type theory, the interpretation of contexts and types is the same, and the interpretation of terms and substitutions is also the same. So this is just a sub m of gamma m to delta m. And we can do this presheaf model, but then there is a and it works in a pretty generic way, but there is some choice that we have to make for Booleans. So we have to decide on the interpretation of Booleans, and the interpretation of functions is already completely given, because in the presheaf model the interpretation of function is just the presheaf exponentials. So the interpretation of AB in the presheaf model, it must be just the presheaf exponentials from AM to BM. But we still have to decide on the interpretation of bool. So if I have a bool which is a type, then the bool M should be a presheaf over renamings. So this means that for every context I want to have a set. So a presheaf over renamings, that means that for every context, so for every gamma, a set such that I can do a restriction along renaming from gamma to delta. So if I have any this, then I can, so the difference is that in the standard model, I only interpreted bool with a set, with just bool. But now I'm interpreting bool with a family of sets. So I have a set for every gamma, which is a syntactic context. So I get a set for all contexts in the syntax, and I get a restriction function for every renaming in the syntax. So this way I get a richer semantics, because now I can do a renaming of things even in semantic values. This means that I get renamings of semantic values as well. And previously there was no renamings. Okay, and but how should I define this? So if bool M is a presheaf, then I have to define all the sets, and I say that the bool M of gamma, so bool M at gamma is just defined to be normal forms in gamma of type bool. And I also have to define the kind of the semantic restriction So if I have renaming from gamma to delta, and if I have a BM, which is an NF delta bool, then so this is the restriction operator which we have seen before, and this restriction is just defined to be substitution. And I can summarize this by saying is that for any A which is a type, this NF A is a presheaf over RAM. So this is a presheaf over renamings. Okay, and now what happens? So, okay, so actually maybe it was a bit unfortunate to talk about. It was a bit unfortunate to have a simple type theory with booleans here. So sorry. Let's instead do a base type. So let's instead, because it's a lot simpler to say that let's just ignore booleans in the simple type theory for a bit, but instead just have a base type which is completely empty. So have a base type, have an empty base type, but we still have this choice. So we still have this choice that we have to interpret the empty base type in some way. And it would be possible to interpret the empty base type with the empty presheaf, but and likewise with booleans it would be possible to interpret the bool with the bool in the presheaf model. But because we want to do this normalization thing, in the end we interpret all the base type formers differently. So if we have this iota, which is a type, then I want to get a presheaf over renamings from the iota, and I just say I just do exactly the same thing as with booleans. So I can say that this is NF gamma iota, and I can say that whenever I have some semantic value and I want to do a restriction along the renaming, then I just perform the renaming as a substitution. Okay, so if I have only functions and an empty type, then actually this picture just works. So I can take a term and just evaluate it in the presheaf model over renamings, and then I can separately just define this function. So I can just define a quote function. So I can just define a quote function by recursion on syntactic types. So the quote function actually is a natural transformation which goes from AM to NF. So this sub M. This means natural transformations in the presheaf model, and because AM is a presheaf and the NF something A is also a presheaf, I can have this natural transformation. So for every A, which is a syntactic type, I get a natural transformation from semantics to normal forms. And I can define this, and at the same time, I also have to define an unquote function. So this is defined by mutual recursion. I want to define two functions, quote and unquote. And the unquote, it goes from it goes from neutrals, so it goes from neutral terms to semantic values. But of course, it's very easy to just remove this mutual recursion by saying that for every type, I just return two functions, and one function is quote part, and the other function is the unquote part. Okay, so I can define this. So the first is just to evaluate the terms, and then the second step is to define quote and unquote, which I'm not going to define now. And then the third step is that we have to prove completeness of normalization, which is actually pretty much the same thing as before. So for canonicity, we say that we do this logical relation between syntactic things and semantic things, and we can do the same thing here. So we again have a relation between syntax and semantics. And now we can also prove soundness and stability. So soundness can be proven by. So how can we prove it? I think soundness is just comes from by induction on terms, and stability also by induction on terms. Okay, so this is simple type theory. But for dependent type theory, we have to do everything in the same time. So for dependent TT, what we have to do is we just go back to the canonicity from previous week. So the canonicity proof in previous week is kind of just doing everything at the same time. So we are defining a predicate. We're defining predicates on closed terms for every time, but it's a proof relevant predicate, so it also, the proof relevance also contains the information for this computation of evaluation. So it's a kind of a proof relevant logical predicate model which performs evaluation and completeness at the same time. Okay, maybe we don't even, I just remember that if we are using this algebraic syntax, we don't have to prove soundness at all. We only have to prove stability by induction on terms. Okay, so if you are using algebraic syntax, we don't have to prove soundness because everything preserves definitional equality. And likewise, here what happens in dependent type theory is that we are doing just one model, and one model performs evaluation and completeness of evaluation at the same time. And for normalization, we have to do one dependent model over syntax, which gives us normalization plus completeness at the same time, which kind of looks like still having these predicates. So a context still becomes a predicate over something, and the type still becomes a predicate. But now everything is kind of so every predicate is not just kind of the set kind of predicate, but it's actually a presheaf predicate. So when we want to do this normalization model, this arrow set, it becomes something similar, but in the presheaf model, and every arrow actually also becomes something similar, but in the presheaf model. So if we want to unfold it fully, then it becomes very, very large and complicated. So that's why it makes sense to just kind of to say that we want to define, or just to specify the model already by working in the presheaf model. So now let's try to define. So try to define. Of course, we will not define it, just maybe write down the interpretations of the sorts in the syntax. So we want to try to define this P model. However, let's say that this M is this kind of interpretation into the pre-sheaf model over renamings of dependent type theory. And actually, we don't just need this, but we also need a variant of the Yoneda embedding. So we also need a variant of Yoneda embedding. And the way that it works, so the usual Yoneda embedding, which I mentioned before, is something which embeds a context into a context in a pre-sheaf model. But the pre-sheaf, so it embeds a context into a pre-sheaf, but over the syntax. So it goes from con. Okay, maybe we can also write it a bit more abstractly. So Yoneda would be a functor which goes from the syntax to a pre-sheaf over the syntax. But now this is not really good because we want to do pre-sheafs over renamings and not over the syntax. So here a morphism is just a renaming, but here a morphism is a general substitution. So instead what we do is do this. So the new Yoneda is something which we can get by taking the old Yoneda and then composing it with this functor, and this functor can be defined just by saying. So we also have like a PHCM, pre-sheaf renaming. So this can be defined by using that every renaming is a substitution. So there is actually an embedding from the category of renamings to the category of substitutions, and we can just use kind of contravariantly this embedding from renaming to substitutions to get a functor from pre-sheafs over syntax to pre-sheaf over renamings. So this is already a bit complicated. So let me just write down the interpretations of the sorts, and then maybe we can move on to something else. So yeah, I warned you that it becomes pretty technical, that if you want to do it for dependent type theory. Okay, but so what happens here is that so this Yoneda, it goes from syntax to pre-sheaf over renamings, and the way it is defined is that Yoneda gamma delta is substitutions from delta to gamma, and then if I want to do a restriction, so if I have a sigma and I want to restrict it with some delta renaming, then it's still just composition. So it's still just composition. I'm not sure if this is the right order, but it's composition because every renaming is also a substitution. So every renaming is also a substitution. So every renaming can be composed with a substitution as well. Okay, and in this case, so for every syntactic context in the P model, which is just this pre-sheaf logical predicate model, which actually contains the computation of normalization plus the completeness of normalization at the same time. So here I get a type in the presheaf model over renamings over the Yoneda of gamma. So predicate. So this becomes kind of a predicate over substitutions into gamma. But it's not just an ordinary predicate because it's a presheaf predicate which also can be restricted by using renamings. And if I have a type over gamma, then what happens here is that here I want to have a predicate over terms of A. But once again, this is a presheaf predicate. So I'm working inside the presheaf model. And here I have, so it's a predicate over Yoneda gamma. So I have some gamma such that the predicate holds for it. And I also have Yoneda A, which we haven't defined. And then this have to be weakened in the presheaf model because Yoneda A depends on Yoneda gamma, but here it's in an extended context. And then a substitution says that sigma preserves the predicates. And how can I say internally in the presheaf model that sigma preserver predicates? I can use a term which is a kind of a dependent natural transformation in the presheaf model. So then I have a term which goes from Yoneda gamma p. So the input is this. So the input is some gamma such that the predicate holds for it. And then I want to also say that the predicate holds for the output as well. But I don't really remember what exactly should be here. Yeah, I mean it should be some delta p substituted somehow with sigma. Okay, I don't really remember this, but probably it's not too important because here we also need to say that T preserves predicates. And you can see that if we are unfolding all of the definitions, so this comes from the presheaf model, so this should be also M actually. So this is context extension in the presheaf model, this is this Yoneda embedding, this is a type in the presheaf model, and this is a term in the presheaf model. So if we want to unfold everything, then it becomes big and pretty ugly. But if you think about it, if we are using these ties and TMs and context extensions and Ps and Qs and De Bruijn indices, then it also becomes very ugly. So we are in the situation is that unfolding all TM is ugly, but it's ugly even if you don't unfold it. So we can actually go a bit further. So there are ways to make it less ugly. So one way to make this less ugly is by saying that we don't want to explicitly mention all these De Bruijn indices and context extensions and types and terms, but instead we only want to work in kind of an internal language of the presheaf model. And in this style, instead of using a type, we say that we are just using a function in the presheaf model, a closed function type in the presheaf model. So this also means that only using close types, universe, close terms in from the species model. And the way it looks is that we are just using a normal type-theoretic notation, but what happens is that although we are just using normal type-theoretic notation, we mean that we are working inside the species model. So here I can say that the gamma p is just a function from Yoneda gamma to set. And then A is just a function which goes from some gamma in Yoneda gamma to, and we also have some gamma p of this gamma, and then we have a Yoneda A and gamma, and then we have a set. And then the sigma, just so here we have a predicate, and here we also have a predicate. And for substitutions now, probably even without looking it up, I can write something which looks reasonable for preservation of a predicate. So if I have a Yoneda gamma, and such that the predicate holds for this, then I also want to know that the delta p holds for what should it hold for? So because the data should hold for Yoneda, then I think maybe this should be a Yoneda sigma of gamma. Yeah, I think that's it. Okay, so in this way we don't have to use De Broglie indices. So no De Broglie indices. But just using normal type-theoretic notation. But what we mean by all these things, so this set is not the normal set, it's the presheaf set, and this arrow is not a function, it's a function in the presheaf model. So is a presheaf function, and set is universe presheaf rem, and so on. And this is a very useful trick, and this is called reasoning, like internal language reasoning, or reasoning in an internal language. But we can also take it even further. So if you want to take it even further, then we can look at Raphael, Christian Sattler, or Taichi Uemura style stuff, and so we can also try to work in an even more advanced style. And in this even more advanced style, we don't even have context most of the time. So here we don't even mention context and substitutions most of the time. And this can be viewed as a kind of a combination of internal languages plus this higher order abstract syntax. And probably this is the best way to do it, but I'm still waiting for the finished version of this so that I can dive into this kind of style, and then probably if I want to do normalization proofs like this, then I would use this internal higher order abstract syntax, and because it takes too much work to work even in this kind of style. And if we want to unfold even this definition of TIM and TMM and so on, then it becomes very, very hard. Okay, that's it for normalization. So I'm not sure how helpful it was. So you can see that it's quite complicated, and but that's how it is. So because it's so technical, that's why there is like a very significant motivation to make it nicer, but there is some nice work to make it easier to handle. But actually, if you want to use this internal language version to prove normalization on your own, or you even want to use the higher order abstract version of this to prove something on your own, then I don't think that you can avoid looking at least maybe once or twice at just examples of this unfolding and just trying to understand like the computation or the behind it, because when we are working, for example, at this level, then it becomes really abstract, and it's probably very easy to get lost if you cannot remember like how can you compile this very high level notation back to the basic definitions. Okay, so any question or anything about this kind of thing? If there are no questions about this, then I think we can move on to, but probably we will not finish it because I think quite a bit of time was spent on this normalization. But let's just move on to setoid type theory, or not setoid type theory. Sorry, I mean just but the setoid model of type theory. Okay, so why do we care about this model, or what is this model? So let's just define first the interpretation of context in this model. And so the interpretation of a context is just a setoid. So if I have a gamma con in the syntax, then in this model the interpretation is just a setoid, but I can just notate it by saying that con is defined to be a setoid. But what is a setoid? So if I'm working in Agda, and I can just switch over to Agda where I have written a bit of a notes. So if you are working in Agda, then this is just a setoid. So a setoid is a set together with an equivalence relation. So here I'm using this bank to denote the set. So this bank is a field. So a setoid is kind of a record type, and then this bank is a field, and then we have an R, which is an equivalence relation on the bank. And you can see that I also have reflexivity and symmetry and transitivity for this relation. But here you can already see that there is a new kind of thing, which probably you haven't seen before, or some of you haven't seen before, is that the equivalence relation returns in prop. So relation returns in prop. And what is this prop? So prop is kind of a universe of proof irrelevant types. So prop, universe of proof irrelevant types. And what does this proof irrelevance mean? So this proof irrelevance means that that whenever I have a type which is in prop, and I also have two elements of this, so I also have A and A prime in A, then I know that A is definitionally equal to A prime. So this means that if I want to prove an equality of things which are in prop, so if I want to prove an equality of an A and an A prime such that both are in A and A is in prop, then I can always prove their equality just by using reflexivity. So every A prime are equal by reflexivity. So they are irrelevant because it only matters that we have some kind of proof for A. So if we have an A which is a proof of A, and we also have an A prime which is a proof of A, then it makes no difference that we have two proofs instead of one, because if we have one proof, it already proves it to be true. So we don't care about getting any other proofs. Actually, if we construct different proofs, then they are all just the same. So they are definitionally the same as the old proof. So for propositions, it only matters that they have some inhabitants, but inhabitants themselves are not distinguished in any way. But we also have a restriction. So the restriction of prop is that we can only compute, prop things from prop things. So this means that it is not possible to get any proof relevant thing out of a proof irrelevant thing. So it is not possible that I get something which is in prop and then sometimes I return like a natural number, but sometimes I return a different natural number. I mean, it's not really possible because these elements cannot be distinguished in any way. So in Agda, the way this prop works is that I'm able, for example, to define bool P, which is in prop. Then it also has two constructors. But then I'm only allowed to return prop things from this bool P. So I can do a not P, which goes from bool P to bool P. And then it still works, but I am not allowed to return a normal. So right now in this file, I think the bool is imported as m.bool, like meta bool. But then I am not allowed to do a pattern matching of this B here. So it says the scanner split on an argument of an irrelevant data type when checking that the expression has type bool. So this doesn't work. And the reason that this doesn't work is that we are not allowed to distinguish things which should be indistinguishable. Okay, and if we are working in Agda, then we can also define like the unit type, but in prop. So this is the unit type in prop, and this is the empty type in prop. And we can also define a sigma where both fields are in prop. So sigma with both fields in prop. And unfortunately, there is no polymorphism over being in set or prop, so we cannot abstract over irrelevance. So whenever I want to use a different version of sigma, then I have to define a different type. Okay, so let's go back to setoids. So this is a setoid. So it has an underlying set together with the relation. And I know that the relation is reflexive, symmetric, and transitive. And if I want to define a model of type theory, then I have to define a CWF such that con is just defined to be setoids. So now I have to define a category of setoids, and I have to define what's a type in setoids, and the substitution, and the P and the Q, and so on. So I have to do this, and substitutions are pretty easy, because these are just R-preserving functions. So a substitution, so a morphism between two setoids is just a function which preserves the relation. And here I'm doing some kind of notational magic by saying that here I'm defining a new record in Agda, but I'm also introducing, it's not necessary, but sometimes as I like to do it, that I'm defining gamma as a private module, so I can use this gamma dot notation without any white space between gamma and bank, and I can just use gamma dot bank to refer to the underlying set of gamma, and I can use gamma dot r to refer to the relation of gamma here. So I'm overloading this bank. So bank is a function between underlying sets, and then r is also overloaded, so it maps a proof of equivalence in gamma to a proof of equivalence in delta. Okay. Okay, and what about types? So this should be, I mean, in any model of type theory, whenever we have an interpretation of the context, so in any model of type theory, whenever we have an interpretation of the context, usually we should have a dependent version of the same thing for the interpretation of types. So this should be kind of a dependent setoid, and and let's just forget about this part, and let's just look at this part at first, because if you look at this part, then it looks exactly like a dependent setoid. It looks exactly like a dependent setoid. So, but let's just give a bunch of examples for dependent things. So there is kind of a generic way of saying what a dependent thing is if we have the definition of a thing. So this can be derived very generically. Okay, so let's just look at some examples for dependent things. So if the thing is just a set, then what is a dependent thing? So the dependent thing is a function. It's a function which goes from a thing to set. So if the thing is set, then the dependent thing is just a predicate. Or maybe let's just write it out this way. So if con is defined to be set, then phi of gamma is defined to be gamma arrow set. So this was the set model. But we can also have like a FAM model. So if a context is defined to be a family of sets, so it is defined to be a set together with the predicate, then the dependent thing, so here I have a gamma and here I have some gamma predicate, is defined to be a predicate over gamma, and then so I get like an A, and then a dependent predicate over this predicate over over gamma. So then it becomes how is it? It was a gamma arrow set. This becomes a gamma plane set. Right. Yes, and this is a set, and this is a gamma set. This is the arrow set. Right. Okay. Okay, but in any case, so if I have an algebraic structure, so if I have a definition of an algebraic structure, then I can usually just derive what is a dependent thing for it. For example, if I have any kind of algebraic structure, I can generically derive what a dependent thing for it. So, for like a simple example for an algebraic structure is a natural number algebra, which is just a set together with a successor function and a zero element. So it's just an A, which is a set. So now I'm not using argand notation, but instead using this because it's a bit shorter. So natural number algebra is a set together with a function and an element. And then if I know that this is the structure, then I can also do a dependent net algebra, which works by, if I already have some A and S and Z, which is a natural number algebra, then the dependent natural number algebra becomes a predicate over A. So I get an AP, which is a predicate over A, and then I have that this S preserves the predicate, so that for every A, if AP holds for A, and AP also holds for SA, and I also have that AP must hold for Z. And if you know about natural number induction, then this could be a bit familiar, because here what happens is that the dependent net algebra is exactly the same thing as a kind of argument to natural number induction. So this is the predicate that we want to prove, and then we have to show that the successor preserves the predicate, and we also have to show the predicate holds for 0. And these are the arguments to the natural number induction, and then we get something, but these are only the arguments. Okay, so with these examples, I only want to illustrate that dependent things can be given automatically for any kind of algebraic structure. And because setoids are also just a kind of algebraic structure, much like natural numbers are, then we also automatically get a notion of dependent setoid. So in dependent setoid, we have a family of sets, or this predicate over the underlying set. And we also have a dependent equivalence relation for this. So for every element of gamma, we have a set. And then for every dependent element of this thing, so for every dependent element of a dependent setoid, so you can see here that X comes from gamma, and this bang X is a dependent element depending on X. And then this Y comes from gamma, and this is a dependent element over Y. And then this is an equivalence proof of X and Y in gamma. And we need all of these parameters to parameterize the dependent equivalence relation of this type, which is a dependent setoid. So if you are used to doing this kind of thing, then you can just write it mechanically, because like for every set you need a dependent set, for every prop you need a dependent prop, depending on all of the previously dependent things. And then you can kind of just do it. And here you can see that the reflexivity is over the original reflexivity, and the symmetry is over the gamma symmetry, and the transitivity is also over the transitivity in gamma. So this is kind of a mechanical exercise, and this is the part which falls out when we do it in a kind of just derive it for me way. Okay, but it's not enough. So if we only do this, then it's not enough. So it's not enough to just derive phi in the setoid model. And why is it not enough? And the reason is that we want, so if we have a gamma, so here we're defining the time, but gamma is already a setoid, and we want the relation in gamma to be so we want the R gamma, or the gamma dot R, which is the equivalence relation in gamma, to be preserved by anything. So if in the setoid model we want this R to be respected by any construction, then we have to say that types must also respect the equivalence relation in gamma in some way. And that's why we need these additional two conditions. So that's why we need something which is called a coercion, and also something which is called a coherence. And if you want to look it up on the internet, so this corresponds to something which is called an isofibration for setoids. And in general, if you want to look it up, so we can have just a dependent algebra, which we get, which is automatic. However, if the original algebraic structure has some internal things which we want to preserve, like an equivalence relation, or in the case of categories, for example, morphisms, we want to respect morphisms in the algebraic structure. When we want to talk about dependent categories in setoids, when we want to talk about dependent setoids, we want to respect the underlying equivalence relation in gamma. So dependent algebra always works in a generic way, but if the structure has some internal additional structure that we want to preserve, then usually these are called fibrations, or different version of fibrations in the terminology. And usually we say that some dependent algebra is fibrant if we additionally know that it respects some structure in the underlying structure, or in the base structure. Okay, so just to be a bit more explicit here, so here we have a dependent setoid, and we additionally want to say that there is a coercion. So the coercion is that if there are equivalent things in gamma, so if x and y in gamma are equivalent, and I have something which is over x, then I want to coerce it to something which is over y. So it's you can view it as an analog of coercion in just type theory when we have this Koi function. So the Koi function is that if we have two types which are equal, then we have an A, then we can go to B. And but we can also talk a slightly more indexed version of coercion. So we can say, which is called actually transport. So if we know that x equals y, and then we have a px, then we can have a py, and that's what we have here. So in any type, if we have an equivalence of xy in gamma, then we can transport from bank x to bank gamma. Okay, and coherence says that that if I have a transported thing, so if I have this this x star, so here my notation is that I'm using a star to denote dependent elements. So here I'm defining what tie is, and an x star is a dependent thing because it's in a bank of x. Okay, so coherence means that if you coerce something, then it's still equivalent to the old thing. So coercion. So this means that coerced thing is equivalent to the non-coerced. Right, so here I have an equivalence, but this is a dependent equivalence. And on the left-hand side, I have this x star, and on the right-hand side, I have the coercion of x star. So x star is still equivalent to its own coercion, but because this is a dependent equivalence between these two things, I also have to mention like what justifies. So I have to mention an equivalence in gamma. So I have to mention an equivalence in the base, and that's this f. So f is an equivalence between x and y. And if you look at the definition of R here, then you can see that, so this is kind of a heterogeneous equivalence, because the left-hand side can depend on a different thing than the right-hand side. However, we still have to provide an evidence that the base things on the two sides are still equivalent. Okay, and then we can try to give the model using this definition of types. So terms are really nothing special because they are just dependent functions preserving R. So you can see here I have a dependent function, and then if I have an R between x and y, then I also want to have an R between bank x and bank y. Okay, and then we can define the empty context. So this is just the one element set. So the underlying set is just a unit, and then the equivalence relation is just a relation which is constantly true. So here I have two things which have type unit, and this should be an equivalence relation, but I just define it to be constantly true because the unit type only has a single element, so I don't have to do anything more interesting for the equivalence relation of the unit type. And then I can just write underscores here. So this should be reflexivity, symmetry, and transitivity. But these are all inferable because I only have functions which return in true, and any function which returns in true can be inferred by Agda because of the eta rule for true. So this true is also defined as a record. That's why it has an eta rule. So any function which returns true is known to be Agda to be the lambda which returns dt. Okay, And for context extension, we are just using sigma to glue everything together. So every component is just pasted together using a sigma. So here you can see that I'm also opening for this abbreviation the module gamma and also the module A. So I can refer to gamma.bank, or I can use gamma.bank to refer to the underlying set of gamma, and likewise for A. So I just take the sigma of them, and then I get a sigma of the equivalence relations for the new equivalence relation, and everything is just pairing. So raffle is a pair of raffle, symmetry is sim, and transitivity is transitivity. Okay, and type substitution is also pretty straightforward. So type substitution can be viewed as a composition of type and a substitution. So here you can see that the underlying set is just given by a composition of these two functions, and the equivalence relation is given by just using the equivalence relation of A, but using sigma to map an F to so here F is an equivalence relation in it's a proof of equivalence in gamma, and then we are using sigma to map it to a proof of equivalence in delta. Is that correct? Or am I talking bullshit? So F is, yes, so F is a proof of equivalence in gamma, and if I'm using the sigma bank F, sigma RF, then I can map it. Because sigma preserves equivalence, I can use the sigma.r to map F to an equivalence in delta. Because A is a type in delta, I can use the A.r x star y star. And here I only need to mention this delta equivalence, so I can use the sigma.r. Okay, and everything else is pretty straightforward. So the way it works is that I'm just using all the things which come from A, but I'm also using sigma to transport elements and morphisms, and incoercion as well. Okay, and then I can continue giving this setoid model for the whole CWF. So I can just continue giving this for CWF, and nothing is very surprising or very exciting when I want to do the setoid model of CWF. Okay, but let's give some words about why this is even interesting, because I remember now that I asked this question, but then I didn't really give an answer to the question. So why do we care? So, I mean, because from previous models, we were able to obtain some kind of meta-theoretic results. And we can also obtain something from the setoid model of type theory. And so the setoid model of type theory can be used to justify some extensionality principles. But the good thing about setoid type theory is that it justifies some extensionality principles, but we've seen, for example, like the standard model also justifies some extensionality principles. But the setoid model, justifies some extensionality without relying too much on the meta-theoretic extensionality principles. So the setoid model is able to, for example, explain function extensionality in a way that we don't have to refer to the meta-theoretic function extensionality. But then this also begs the question of why do we care about this? And cannot we just simply use all the meta-theoretic features to explain everything, and then we are absolutely happy? But this can be a good thing, because if a setoid model can justify, for example, function extensionality without relying on function extensionality in the meta theory, then it means that we somehow have to build some machinery to make this possible. So if we are not just simply using all the meta-theoretic features, then this can be actually used as an implementation of extensionality features, and not just simply referring to something which already exists in the meta theory. So it's kind of an implementation of extensionality features, and because this has more structure and more machinery, this can be used as inspiration or kind of a hint to implement syntax for a type theory which has these extensionality features, but which is also computationally adequate theory. So it can be used as a hint to implement syntax of TT with extensionality principles, but such that principles are not axioms, right? So if we are working in Agda, we can always just simply do a postulate and just say that function extensionality is an axiom. But the problem with axioms is that you cannot use your language as a programming language anymore. So if you have an axiom, then there is no computation rule for how the axiom should be evaluated or should be reduced. So one possible thing which you can do is just say that we have MLTT plus function extensionality as axiom, and then we can use standard model to prove this consistent. Right? So this works. However, this language, so MLTT plus Phonex as axiom, is not a programming language. Because there is no computation rule for axioms. So if you are working in this language, we can write a program such that we try to evaluate it, but at some point we hit an axiom. Like, for example, with the transport over Phonex, and because transport over Phonex never evaluates to anything, then the program cannot be run further. So we can already do axioms which are justified by some model, and we can still write proofs in it and use it as a logic, but we cannot use it as a programming language. And then the setoid model can be used to justify Phonex in a way such that we can still use some syntax of type theory as a programming language. But the setoid model does not directly give us this thing. So we do not directly get a programming language with Phonex from the setoid model. But we can kind of derive a programming language. So we can take it as an inspiration. to define that language. Okay, so in setoids, we can get these extensionality principles because now we say that a type is not just simply a set. So intuitively speaking, a type is not just a set of things, but a set together with an equivalence relation, and we have the freedom to choose the equivalence relation to be more interesting. So we are free to choose all the R to be interesting. So in the standard model, when every closed type is just interpreted as a set, then we are forced to reuse the meta-theoretic equality to be also the semantic equality. So in set model, we are forced to use meta-equality for semantic equality. But in setoid model, we can choose whatever we want as long as it works out in the model. Okay, so for example, in the setoid model, we can just choose the R of functions. So for example, we can choose equality, so this R of functions to be pointwise equality. Okay. Another example is we can just choose equality. So assuming that we have a type theory which contains a prop universe, equality of equality in prop to be just logical equivalence. So whenever I have two type in prop, then I say that okay, let's just write it out. So if I have A, B in prop, then I say that that A is equal to B if and only if there is a function from A to B and there is a function from B to A. And this is also so this is a function extensionality principle, and this is called the propositional extensionality principle, and it is also pretty nice if you can have this principle. Or we can say that choose equality of codata. So whenever we have co-inductive type in the setoid model, we can choose the equality of codata to be by simulation. Probably this also requires some explanation, but like one specific example is that what should be, so when should two infinite streams be equal? So a specific case is equality of infinite streams. So in Haskell, probably everyone is familiar with this kind of infinite data structure. So we can just define the stream of A to be the cons of A and then the stream of A. And then the stream extensionality. So stream extensionality says that the two streams are equal if their heads are equal, and co-inductively the tails are also equal. So if I have S1, S2, stream A are equal if and only if head S1 is equal to head of S2, and co-inductively tail of S1 is equal to tail of S2. So this co-inductively here means that this relation is defined. So this relation itself is defined by co-induction. So you can view that the equality of streams is given by an infinite stream of equalities. So inequality of streams is a stream of inequalities. And we can use the setoid model to justify all of these kind of things. And in some cases, we can even justify principles like this if the meta theory does not have the same principles. So we can use the setoid model to justify function extensionality even if the meta theory does not have function extensionality. Okay, so I'm not sure. Maybe we can just continue until we have time. So in this Agda file, I only wrote something about the interpretation of Booleans, and also I just started to write at the interpretation. But probably I can summarize the interpretation of Boole in a more compact way than here in the Agda file. Okay, so for Boole, we want to have a type in any gamma. So this Boole should be a dependent setoid, but actually, because Boole does not depend on gamma in any way, we can just define Boole to be a normal setoid, and it is also possible to have these constant types. So in the setoid model, it is also possible to define non-dependent types or closed types just simply as semantic contexts, and then use this K operation to turn them into types in arbitrary contexts. So here it is possible that if I have some context, then I turn it into a type in an arbitrary context. So for Booleans, I only have to define a setoid, and I just say that the underlying set of this setoid should be, so the bool.bang is just defined to be Boole in the meta theory. So meta theory in Boole, and then the relation is just defined to be the propositional. Okay, actually, it's not just the usual proposition equality of Booles in the meta theory, because now, if you remember, so the equivalence relation for Booles should be a Boole arrow prop, and we can define it by case distinction of Booleans. So we can say that true is true. And false is also true, and in other cases it's false. But here this true, so this big T true is the true proposition, and this big T false is the false proposition, while the small T trues and falses are inhabitants of the Boole type. Okay, so we can just define Boole to be like this. And if we define Boole to be like this, maybe if we look at the Agda file, you can also see that it's pretty much the same thing. So here I'm using co-pattern matching to define the fields of this record. And the bang of Boole is just the meta-theoretic Boole, and then the relation is given by this pattern matching. And all the reflexivity, symmetry, transitivity can be also given by pattern matching on the Booleans involved. So this is just a proof that this R is actually an equivalence relation, and coercion and coherence are kind of trivial because the Boole does not depend on the environment. So in this case, the coherence just becomes essentially the same thing as the proof of reflexivity. Okay, and then we can define true and false, and we can also define the eliminator for bool, which I haven't finished, but it should be kind of straightforward. So if you have so this is the type of the eliminator. If we have a type which depends on a bool, and then we have a case for true, and we also have a case for false, then we have a case for every booleans. And if you remember, these terms are essentially all functions which preserve R, and in the end we also want to return a function which preserves R. So here you can see that the underlying function in the output is defined just by using case distinction in the meta theory on the result which we get from using this B. So this B is an R preserving function, and then we just use bang B to apply this function on this element of gamma. Then we get a Boolean, and then we do a case distinction on it, and then we have to repeat the same case distinction for R, and also we can use the symmetry reflexivity. Sorry, we don't even need to do anything with symmetry reflexivity transitivity here, because these are the only two components. So we just have to do this case distinction, and then we also have to do it do the same thing to define the action on R. And then we also have bool elim substitution and true substitution and false substitution, but it's also doable. Okay, so should we continue with this pi here? I spent quite a bit of a time on this normalization, so I was not able to progress a lot with Satori type theory, and here I was also doing a relatively long-winded explanations. So should we start the pi now, or should we leave it to some next seminar?
I think we should stop now. And maybe we should discuss what to do next time. Because I think we covered basically everything that we wanted to. No? Or Raphael, is there something that you would like to talk about?
Yeah, I don't know. I mean, maybe I could talk about the groupoid model, maybe, or something like this. I don't know if people are interested.
Yeah, I think that would be good. Yeah.
This would be the next step after.
Like the next level after the scatoid model. Mm-hmm. Yeah, maybe about the groupoid model, and maybe a few words about the cubical set model or something like that, just very informally.
Mm. Yeah. Are there things missing in the Setoid model?
I'm not sure. I mean, maybe it was a bit of a mistake just to talk about bool, because it's not too interesting. I mean, with pi here, we get these slightly more interesting things when we say that R is a pointwise defined. And here, I mean, pi, it's maybe it's a bit more interesting technically, that here we have to use coercion and coherence in order to be able to define this. And here we can see that it doesn't work without having this this coercion and coherence. But I think probably it's also a bit technical already. But it does not get better from now in this sense. So it's only get even more technical if you even move to the groupoid model.
Yeah.
Okay. Okay, then we'll see, but I think then the next week will be the last one in this series. Okay.
Okay, then I
Yes,
stop
thank
the
you very much,
recording.
András.